Hello, welcome to everyone in this video. This is our lecture number 2 on statistical mechanics. In this video, I want to discuss about the microcanonical ensemble. That include the postulates of equal a priori probabilities, Boltzmann hypothesis, that's the relation between entropy and the thermodynamic probability. So you can see the syllabus of Calcutta University for the physics honor 5th semester statistical physics. In the first lecture we actually discussed this portion, that is the, you can see here, that is the classical statistical mechanics. In the first part we discussed the macro and microstate, elementary concept of ensemble, periodic hypothesis and phase space. This already discussed in the previous lecture. If you want, you can go through the description log, the link are given there for the playlist. In this video, I want to discuss this portion, that is the microcanonical ensemble, postulates of equal a priori probability, Boltzmann hypothesis, that is relation between entropy and the thermodynamics probability. Okay, so let's start. This is the total syllabus we will be covered up in the upcoming session. Let's know the microcanonical ensemble. In the previous lecture, we already discussed with the concept, that's the microcanonical ensemble, canonical ensemble, and the grand canonical ensemble. In microcanonical ensemble, they are the isolated system. Canonical ensemble is the closed system, and the grand canonical system is the open system. Okay, so microcanonical ensemble, that is the isolated system. Here the no energy transfer between system and surroundings, and the no particle, that is the number of particle also constant. So here the macro state is defined as the n, v and e. These are the constant of a macro state. So n is constant, which means the particle cannot penetrate, impenetrable in this wall. So this wall of the system is impenetrable. Next, v is constant, that is the wall of this system is rigid. And third is the energy is constant, that is the energy not transfer the system with the surroundings, that is the adiabatic wall. So this is the nature of the wall, that is the impenetrable, rigid and adiabatic. And this is isolated system already discussed. Here the reading variable is the entropy. In the microcanonical ensemble, entropy is the leading variable. After obtaining the entropy, you will be get the different thermodynamics variable from the entropy. Sometimes also take the internal energy as the leading variable, but actually entropy is the leading variable in the microcanonical ensemble. Okay, so if you obtain the entropy, you will be obtain another thermodynamic variable will be discussed in this video in the last part. Now you know about how you will be find out the microstate. For example, if you have a n particle, and from that you will need to select the r number of particle. So the number of possibilities of the way is ncr. This is the number of microstate of this occurrence. Next, if you have a n particles, and you need to select the r particle and placed in the m places. That means you select the r particle from this n particle and this place in the m places. Okay, so there is a combination, that is ncr, and there also a combination mcr. So the product of these two phenomena, because these are dependent occurrence, when the two phenomena is depend, they are product. When they are independent, they are sum in the probability nature. This is the nature of probability. So the number of microstate will be multiplicative of this system. Next one is the number of microstate of to n spin s particle. So spin is s and there are n particle. So that is total number of spin 2s plus 1, and that is whole to the power n. This is the number of microstate. So this is the number of microstate in different case. Go to the next case. That is says number of microstate to fill a ni particle in gi place. There are gi number of places, that is called degeneracy, and the ni number of particle. Then the number of microstate will be different in case of different statistics. In Maxwell-Boltzmann statistics, this will be like that gi whole to the power ni. Gi is the total number of energy level after considering degeneracy. In Bose-Einstein statistics, this will be ni plus gi minus 1 whole factorial by ni factorial into gi minus 1 factorial. This is for boson particle. You know, for boson particle, they does not obey Pauli principle. They are quantum mechanical, and they are indistinguishable. Similarly, for Fermi-Dirac, these are indistinguishable quantum, but they obey the principle, Pauli principle. That's mean with the same energy state, only one particle can exist. Okay, so this will be like Gi factorial by Ni factorial, Gi minus Ni factorial. So you need to remember these three distribution law. You can easily find out the number of microstate in the Maxwell-Boltzmann or Bose-Einstein or Fermi-Dirac distribution. So this is the important slide for you for the question asked in the examination based on this distribution or the number of microstate. You need to find out the number of microstate for different distribution, and you need to put out this formula. Just that's it. Next is the number of microstate in phase space. Phase space means the momentum position space. Okay. So the number of microstate will be total volume in space and the unit cell volume. This is the number of microstate. Total volume available within this phase space divided by unit volume is the gives you number of microstate. Okay. So in case of 3 dimension, this will be a 1 by HQ, this one, and this is the volume in real space, and this is the volume in momentum space. In 2 dimension, this will be like that. This is area in real space, and this is the area in momentum space, and 1 dimension like that. Actually, the formula will be like that. There is a multiplication of GS. GS is the degeneracy factor. So this is the actual microstate in the phase space diagram. So in phase space diagram, the number of microstate will be GS integration D of F Q and D of A and H to the power F. F is the degree of freedom. The Q is the position, generalized coordinate, and P is the generalized momentum. Next thing, there are two microstate, then their addition. Actually, the combined effect will be multiplicative. Number of microstate will be multiplicative. Okay. Next one, number of microstate in energy interval. If you have a energy interval E to E plus dE, the number of microstate will be like that. Okay. So the density of state is nothing but divided by this one. So omega prime E, and this variation will be like that. The if E is proportional to P to the power S, P means momentum and Q means generalized coordinate. So the omega, that is the number of microstate, will be varies at, and the density density of microstate will be varies like that. Okay, so this will help you to draw the mathematics. Next point is called the postulate of equal a priori probability. This is the important postulate for the statistical mechanics, and this is the fundamental property. Actually, says postulate in the statistical mechanics says that a system in equilibrium has equal probability to exist any of its accessible microstate. Suppose this is a system with a single macrostate with defined microstate, and the probability to obtain the microstate will equally probable. That's the postulate equally probability. Here written as it is known as the postulate equal a priori, and fundamental postulate of this. The probability of given macrostate will be the proportional to the number of microstate is contained. That means the probability of the macrostate actually depend on the number of microstate. If the number of microstate is higher, then the probability to obtain the macrostate will be also higher. That's the postulate. And the probability to finding the phase point for a given system for any region of phase space is identical with respect to other region of phase space. That's been any point. If you find the phase space or any point within the phase space is identical to every point. That's the postulate. Next is the important thing, that is Boltzmann hypothesis, which says the relation between entropy and thermodynamic variable. You know, entropy is the thermodynamic property, that is the macroscopic property, whereas the thermodynamic probability, that is the microscopic property, statistical property. So this is the interlink between the thermodynamics with the statistical mechanics. Okay, that's mean the relation between macroscopic property with the microscopic property is the relation of the Boltzmann hypothesis. So this relation between the macro state, that is the thermodynamic variable, with the micro state, that is the microscopic parameter, that is the statistical variable, actually this is the Boltzmann hypothesis, that is S equal to KB ln omega. S is the entropy, Kb is the Boltzmann constant, and omega means is the number of microstate. So this is actually the relation of the Boltzmann hypothesis. You just know about these two things, that is the volume in d dimension will be pi to the power d by 2 r to the power d by d by 2 whole factorial, where r is the radius, and the area will be 2 pi to the power d by 2 r to the power d minus 1 by d by 2 minus 1 whole factorial. You need to remember these two to find out the mathematics. So you need to prove that relation that S equal to Kb ln omega, which is the Boltzmann hypothesis. That is the relation between entropy and the thermodynamic probability. Okay, so you consider a system of the maximum entropy with the maximum probability. So you can take this as proportional to f of y. F of that is a function of microstate. So the entropy of the system depends actually the number of microstate. So you can taken as the S entropy is equal to function of omega. Now we consider two independent system, that's entropy S1 and S2 with the probability omega 1 and omega 2. So their combination will be like that, S12 equal to S1 plus S2, that is omega 1 omega 2, their product. So if you just put this value these two and taking the derivative, and after multiplying these two things you will be get this is constant. So you will take this omega a prime omega equals to constant. So just integrating two times you will be get this relation. Now put the relation, that is the thermodynamics third law, which says at 0 Kelvin temperature the entropy will be 0. So at 0 Kelvin temperature all are aligned in a single state, that's the number of microstate will be 1. There are no difference in the different state, there is only one state, that is the number of microstate will be 1. So if you put this value, this k2 will becomes 0. So the relation becomes x equal to some constant ln omega. Now you need to find out the value of k1. Okay, so for that you just consider a isothermal expansion is carried out in which the volume of an ideal gas containing capital N molecules changes from V1 to V2. That is the volume change from V1 to V2 and corresponding entropy change S1 to S2, and the probability number of probability will be omega 1 and omega 2 respectively. So their change will be like that, and in isothermal process the change entropy change will be like that. So this is the formula which already obtained in thermodynamics, and this is the formula we just take here. If you compare these things you will be get, that is the k equal to r by n, that is kb, all Boltzmann constant. So this is the important formula you need to derive in the different question. Actually this type of question asked in the uh, university examination, so you just practice this one. Okay, now we already says that from the leading parameter, that is the entropy, actually used to find out the other thermodynamics variables. Like you already obtain S equal to kb and omega. So you use the first and second law of thermodynamics, that is dq equal to dds plus du plus pdv minus mu dn, where u is the internal energy, p is the pressure, v is the volume, mu is the chemical potential, n is the number of particles. So if you take the derivative with respect to u, so you will be get ds by du, and the others are constant, so this will become 0. So from here you will be get the value of T, temperature. If you take this derivative with respect to v, where u and n are constant, so you will be get the expression of pressure, and you can see there are the T, or which T actually obtained before. Similarly, if you take derivative with respect to n, u, v and n, there is a three variable. So from that you will be the obtain mu. So you obtain T, P and mu. Using this thing you can also obtain the internal energy. Internal energy actually obtained from the rearranging this function, because the S, that is the entropy, is a function of N, V and E. So just rearranging them you will be get obtain the internal energy. From that you will be get enthalpy, that is H equal to E plus PV. U is obtained here, P and V already obtained here, P and V is the constant here. And the Helmholtz free energy F equal to U minus Ts. T is obtained here, and U is obtained here, T is here, and S is given. Similarly gives free energy. After that the specific heat at a constant volume, that is dq by dt, because here the volume and number density are constant, so these two are 0, so dq equal to du. So Cv equal to du by dt at constant d and du. Similarly, for constant pressure, this dq equal to like that, this will be 0. So you will obtain this one, and since constant pressure, so dp equals to 0. So you can take additive this one, and this result u du plus pb. Okay. So this is the h. So Cv equal to du by dt and Cp equal to dh by dt. Du, u for internal energy, h for enthalpy. So their ratio gives you like that. Okay. So up to that point, we take the leading parameter, that is the entropy. Now if you take the leading parameter, that is the internal energy U, so you just change the S with the entropy and take this integration. You can see if you take this with respect to S, this is gives you 1, this is du by ds. Okay. If you with respect to V, others are constant, so this is 0, this is 0, you will be get this one, and in case of n, take others constant, you will be get this one. So this also the relation in terms of entropy, internal energy. Before one was the entropy, this is the internal energy. Now after that, using this formula, enthalpy, Helmholtz free energy and Gibbs free energy, then Cv, Cp, gamma, you will be get the same result, same types of result with the expression of internal energy. I think clear. Now just look into the some previous year question. In CU 2021, they asked the entropy of a black body radiation is given by like that. You need to prove this one. So you have the value of entropy. From that you need to find out the pressure. So entropy to pressure, you can see here entropy to pressure can be obtained using this formula T ds by dv. Okay, so directly you can use this one, no problem. Otherwise you can change into E and then find out. Okay, change into E and then find out del u. Otherwise you can take this simply derivative. You can see here del, okay, p equal to t del s del v, p equal to t del s del v, p equal to t del s del v, p equal to t del s del v. If you just take, there is a connection problem with the pentaf, I think. If I solve this problem at this moment, then I can write on that. Okay, I think solve. So p equal to del s del v, just forget this one at this moment. So p equal to t del s del v, t del s del v, u and n constant, del s del v, del s del v, u and n constant. So del v with respect to v, if you derivative, that is 4 third sigma with respect to v, so v to the power minus 3 by 4, e to the power 3 by 4. Okay, so this gives you 1/3. Okay, no problem. 1/4, 1/4, okay, 1/3 sigma, and this gives you v to the power 1/4, then there is a v e to the power 3 by 4. You can see sigma into v to the power 1/4 is gives like that 1/3. You need to find out pv, and you need to replace this s, but this is actually problematic here. So if you take 4/3 and there is 1/4, this gives you actually s by e to the power 3 by 4. So e to the power 3 by 4 b. So I think this is not the right process. Okay, so you need to find out the energy, and after that you use this formula, you get this relation. Okay, next question says, assuming the entropy S is a function of the number of microstate omega, so that the additive character of S, that is the entropy, and multiple character of omega, that is the thermodynamic probability, gives this relation S proportional to ln omega. as the entropy is additive and the omega is the multiplicative, so this must be logarithmic function, because in case of logarithm the multiplication change into addition summation. So they have considered the two system S1 and S2 with probability omega 1 and omega 2, so composite system will be like that. And since s is a function of omega, so just put this value, you'll be get this one, and this derivation we already obtained. So just taking the first derivative and combine these two things, finally you'll be get this already discussed just before. Next question says, for a single spinless non-relativistic point character of mass small m confined in a volume V in 3D having energy E and E plus dV. So write down the necessary region per volume of the space. So accessory region is that is the density, space density 1 by h cube, this one, and this is volume V and this is the momentum. So momentum change into the energy like that, p square equal to 2me, so 2p dE equal to 2m dE, so dp equal to m dE by p. Finally you will get this one, so put this value, you will get this one, and this is for integration gives you total value, but here the energy range E2 dE, so this will be the formula. I think you clear about that part of the statistical mechanics with this previous year solution. If there is any doubt, you must comment in the comment box. This is all about me, and this is my contact detail. You can connect me with this Telegram channel, and this is my YouTube channel details. Go to this channel, you will get different related video, some mathematics like this session. If you learn something from this session, share this video to your friends, either he or she also get benefit from the video. Subscribe this channel if you new in this channel. Those already subscribed, thanks for subscribing. Press the bell icon to get notification of upcoming video. So take care. We'll meet on the next video as soon as possible. Thank you.